I think we're ready to start. Thank you everyone for joining us today. I'm Jessica Finnegan with Nullspace. Welcome to part 3 of our 3-part webinar series from RF simulation to 3D printing. In today's webinar, we will demonstrate efficient techniques for creating antenna and GRIN lens geometries using Nullspace Prep. The presentation will feature a detailed case study, a walkthrough of the simulation process, and a comparison of the simulated and measured results. Today's presentation will be given by Dr. Daniel Faircloth, who is the CTO at Nullspace. Today, we also have Masha Petrova, who is the CEO of Nullspace on the webinar.
Welcome, everyone.
At the end of the presentation, Daniel will answer any questions that we have time for. So please post your questions into the Q&A or the chat at the bottom of your Zoom screen as they come up during the presentation so we can address those at the end. And with that, I'll turn the time over to Daniel.
Okay, thanks. Welcome everybody to part 3. As Jessica said, just type your questions in the Q&A. If you have any technical difficulties, you can get to us at webinars@nullspaceinc.com. If you're just joining us, we've been doing a 3-part series here in partnership with Fortify, unique RF additive manufacturing company that we're partnered with. As a bit of background on Nullspace, if you're just now joining us in this webinar series, Nullspace technology was developed at a company called Iris Technologies, which was an established US-based defense contractor. And Nullspace was really born out of the need for having next generation RF simulation technology to support the design and analysis of new and novel RF technologies. The software has been in development for over 12 years, and Iris spun it out as Nullspace last year, and we're bringing it to the world now. So our 2 main products are Nullspace Prep and Nullspace EM. Nullspace Prep is a CAD and meshing preprocessor, has a GUI for CAD creation, manipulation, import, export, etc. But really one of the most powerful features of it is its Python API that allows you to completely through Python control all aspects of the CAD, whether it's creation, cleanup, defeaturing, and it provides a really nice capability for design optimization, which is some of what we'll be talking about today. Nullspace EM is the actual EM simulation engine. It's been designed for capturing all of the relevant EM physics and accurately representing the geometry that you're actually trying to simulate. We support multi-CPU and multi-GPU acceleration, and what makes Nullspace EM really unique for large-scale simulation and optimization problems is our compression algorithm. So the basic workflow for Nullspace Prep and Nullspace EM looks something like this. So you have an idea, you have some customer requirements, existing CAD, you bring that into Nullspace Prep and create the geometry or manipulate the geometry, create the mesh, assign material properties, etc. And Nullspace EM, through the Python API, you configure that simulation. And then we have a variety of methods for post-processing that allow for a lot of flexibility for integrating into customized workflows, whatever workflow that you have that's most convenient for you. Almost certainly our data formats and the way that we provide the ability for users to interact with that data can fit into your workflow. And throughout the entire process is the Python API that underlies all of this that allows for some really powerful parametric analysis, optimization, uncertainty quantification capabilities. So the topic that we've been addressing over the series of webinars and that we're focusing in on today is GRIN lens design with Nullspace. GRIN lenses are gradient index lenses, so they have variable permittivity throughout the volume of space. Here I'm showing a Maxwell fisheye lens sitting on top of a phased array that we have designed and simulated with Nullspace. So you can create some pretty novel geometries that provide some unique RF capabilities that are fairly atypical, and we'll talk through some of that today, both from the perspective of the power of GRIN technology and how using a tool like Nullspace and in partnership with a company like Fortify and their added manufacturing capability, how you can yield some of these really unique designs. And we'll go through a couple of examples. So, as an RF engineer, we think about designing in the context of real world constraints. I need to create a high performance design, but I have to consider other requirements. And the Dream Airplanes cartoon is kind of a classic example of how all different engineering groups, have different perspectives and priorities on different aspects of the design. And it's no different in the RF space. We have non-RF requirements and even RF requirements that are placing constraints on the design space accessible to us. And we have to consider things like, size, weight, how an antenna, for example, is going to get integrated, into a larger platform, whether that's a car or an aircraft. We have to consider, of course, RF performance factors, power handling, gain, bandwidth. How are we actually going to fabricate it? What's the methodology for fabrication? How long does it take? And of course, in the real world, we are very concerned with the cost aspects. What are the non-recurring and recurring costs associated with how we have created this design? It has to go out in the real world, so there are environmental factors and so many other things. Then on top of all those real world things, we have to consider the design space that we're giving ourselves to create the design. So how is that geometry represented? What is the topology that we're using for representing that design? And so lenses in general, as a concept, they provide a useful new kind of design freedom. So once you introduce the idea of making use of a lens, you have, a lot more flexibility to play with, different ways of achieving those requirements while also recognizing, that the non-RF requirements need to be met as well. So we want to have as much freedom as possible. Lenses are just one way to introduce that additional freedom. And then GRIN lenses on top of that provide even more freedom. So, traditional lens, just like you think about your eyeglasses or any other sort of optical lens, they use shape and the dielectric of the material for that lens to manipulate the fields. And so, you have kind of the conventional spherical lens shape or A-sphere lenses and things like that. And, whether you're designing in the optical regime or the RF regime, those design rules are pretty well known, and what you can do with that, provides some interesting capability. But then if you add in the concept of gradient index, now you're adding in spatial variation to the material properties, and that's giving you an additional piece of design freedom. And it's really, to me, kind of introducing this concept of maximizing the utility of a given electrical working volume. I have a physical volume, of course, that I need to work with, but that physical volume, when you translate that into wavelengths and think of it in terms of the electrical volume, physics has something to say about what you can achieve with that volume, and we want to make the best use of it that we can. And so GRIN lenses add in a really powerful capability for doing that. And so there's some classic lens types, or a lot of people have heard of Lundberg lenses or Maxwell fisheye lenses, and they leverage, they're both spherical shapes, and they leverage a gradient in the index of the refraction to, focus a plane wave down to a point on the lens. In the case of a Lundberg lens and a Maxwell fisheye, focuses from one side of the lens over to the other. And as an interesting use case, if you truncate a Maxwell fisheye lens, like we've done over here, you can interface it with geometry like this phased array that I showed earlier, and you can get some interesting beam steering capability out of that phased array when it's enhanced with the lens. So we're we're adding in some new design flexibility, of course, some new way of thinking about how to use that flexibility by leveraging spatial variation of the dielectric material within a given working volume. So there are a lot of different kind of classic GRIN lenses. There's the Lundberg lens and Maxwell fisheye that we've already talked about. There are Eaton lenses. There are some interesting kind of quasi-analytic ways of designing those lenses, like quasi-conformal transformation optics, for example. But when you boil it down, you have a shape, you have some gradient of the dielectric, and really, you have a lot of freedom in how that gets specified. Of course, using one of the classic lens types, there's a kind of a formulaic approach to those lenses. But as we'll see throughout our discussion today, there can be a lot of unique capability by kind of opening up the aperture, so to speak, on how we do the design, how we allow that permittivity to vary. And one of the key things enabling that is the Python API that I've already mentioned, that's used throughout Nullspace Prep and EM. So that's going to empower you to create geometries that are atypical, that are novel, and they can be coupled with an optimization capability to yield some pretty incredible capabilities. So the typical way, that a user might specify one of these gradient index regions is either through a point cloud, where you have sampled the permittivity within the volume, and you want to convert that into some kind of inhomogeneous dielectric representation. You can also represent as a series of layers. We've got two examples here on the left and in the middle of a Lundberg lens represented as a series of shells, and that Lundberg lens is being illuminated by an open-ended waveguide, which is a common excitation for a Lundberg lens. And even just within this layers representation, you can see we've got, layers of equal thickness, layers of unequal thickness. So there's already, introducing this idea that there's a lot of flexibility, even within just the constraint of a Lundberg lens itself. And then, in addition to layers, we can go to voxels, and you see that a representation of that on the right, where we have discretized space into equal-sized voxel cells, and just sample the permittivity within each voxel. And once we have a framework for doing this, then I think your imagination can start to go in a lot of different directions about how you could design some pretty incredible gradient index media and interface those with different antenna structures. So in general, the lens design workflow, goes something like this. So we set a working volume, whatever kind of physical volume constraint that we have. We decide on a representation for that GRIN lens. Is it a point cloud, Are we going to use layers? Are we going to use voxels? And then eventually, in terms of how that actually gets represented in Nullspace Prep in the CAD, we're either, even when we go through a point cloud representation, we're converting that into a layered or voxel based representation. And here I've shown a layered representation of a Lundberg lens, but the layers don't have to be spherical. It could be any sort of isosurface type representation. And that's just up to your creativity as to how you might want to specify that. So we set some topological representation of those layers, how many layers, sample the permittivity in each one of those layers. On the voxel side, we're setting sort of the basic size of a voxel, creating that initial grid of voxels, and then sampling the permittivity within each voxel. Once we have that, we can create a material library, and that material library will be fed into Nullspace Prep to actually generate the geometries, like you see here. Then we simulate, and if we're doing a design optimization, we're going to come up with some fitness metric. Maybe we're trying to maximize bore side gain, for example. We'll evaluate that fitness and then adjust parameters. And those parameters could be the permittivity in each voxel or in each layer, or maybe even you are optimizing based on the number of layers. So there's a lot of design flexibility that can be had there. So just looking at a voxelized Lundberg lens, one of the nice things about using a voxel approach is it naturally aligns with how an additive manufacturing print process works. So as Phil discussed in the previous webinar, and we talked about a little bit in the first webinar in the series, the actual printing is done with a gyroid unit cell. So there's already this kind of natural voxel representation in the print process. So if we represent our geometry in Nullspace using a voxel approach and do a design optimization based on that, that's aligning very well with how the actual fabrication occurs. When you think of voxels, especially as we've got shown here with different sizes of voxels, you can see, there's some discretization error. This 0.8 lambda Lundberg lens representation, it's obviously not a sphere anymore. And, there are a couple ways to handle that. You could either, maybe from an electrical perspective, it's not even necessary to handle that. And we'll take a look at that on the next slide. Alternatively, there's nothing restricting you from using partial voxels. So you could still have the true spherical shape, and you would just have some partial voxels, rounding out the geometry. But as is alluded by this picture here, there's kind of this question of what is the optimal voxel size, and I think you have to look at that from a couple of different perspectives. One has to do with the gyroid unit cell involved in the printing process itself, and we'll touch on that in a little bit. And then there's the electrical representation, and that gets into a little bit of, in the case of this example that we're looking at here, which is a Lundberg lens, are we trying to represent a Lundberg lens, or are we trying to achieve a certain RF performance with a given voxel size? Those are really two different ways of looking at the problem. We also want to consider fabrication tolerances and constraints. So as was discussed in the previous webinar, Fortify uses the Radix 2.8 and a couple of other materials, and the accessible permittivity range varies with different unit cell sizes, and there's a kind of a minimum constraint of a permittivity of 1.2, so we need to factor that in. So in these representations here, we've already accounted for the fact that that we would limit the index of refraction or the permittivity to 1.2, and we would just remove any voxels that don't meet that criteria, and that we remove any voxels that are outside the spherical profile. So let's look at this question of, how does the performance vary with these different voxel sizes? And here we're showing the gain pattern in the two principal plane cuts, the E and H plane for that Lundberg lens. And you can actually see even, it's a bit, non-intuitive, I think, even with a unit cell size up to 0.8 lambda at the bore site, there's less than 1 dB of total gain variation across all these different resolutions. And if we go and dig into the analysis, the dominating factor in this 1 dB variation is actually that staircase representation of the outer edge of the spherical lens. So if that's not really something that you're concerned with, you can just tweak, parameters of those voxels. I think more interestingly is the variation in terms of side lobes. I think it's not very surprising that the more coarse representation of the voxels has larger side lobes. And so that would be something that you could take into account in your design. So there's already some interesting evidence here that you can use fairly electrically large voxels to represent these arbitrary shapes and get good performance, from these types of lenses and when represented as a voxel grid. So here's another example that we did in partnership with Fortify. This time, still looking at a Lundberg lens, but a layered representation. So we took a 6-inch Lundberg lens, Fortify printed it with radix 2.8, and it was large enough that they actually printed it in 2 halves, as you can see the top half there and the top right, and assembled it together, and you can see the measurement set up down on the bottom right. Bottom left, we see the 3D gain pattern at 22 gigahertz as predicted by Nullspace EM. And when we look at how this layered representation matches up with the measurements, we see that there's very good agreement. So we did a comparison between Nullspace EM, CST, and measurements, and Nullspace EM was right on with the measured result using a 7 equal thickness layer representation. So even though a Lundberg lens technically has a continuous variation, sort of in the ideal sense, there's not really a reason to do that, and you can get good, still a Lundberg-like performance out of that multi-layered geometry. Okay, so let's take a look at, the main case study for the webinar. We want to look at a zone plate lens versus a GRIN lens. So for those of you that may not be familiar or may have forgotten, a zone plate lens, it's a classic structure that uses a staircased shape. It's made out of a solid dielectric material, and it's kind of a flat lens type geometry. If you look up Fresnel zone plate lens, you'll see these staircased kind of representations of a flat lens. And then a GRIN lens typically uses a fixed shape and varying dielectric to provide the focus. So it kind of raises the question, if I'm going to use the same working volume, is there a performance benefit for GRIN versus a zone plate lens? One is from a fabrication standpoint, zone plate lens is solid dielectric. You could machine it. You could also 3D print it, and that we've done that in this case. So is there a performance benefit by adding in the additional variable of having spatial variation So in our case study, we're going to look at a 16 gigahertz patch antenna that's feeding one of each type of lens. We're going to design the lenses to have the exact same focal distance and to occupy the same cylindrical volume so that both antenna assemblies, when fully put together, they occupy the same total volume. We're going to look at return loss, peak gain, and gain patterns. So first off, let's just look at the patch antenna by itself. So we've got a 16 gigahertz coax fed patch on a Rogers RO3003 substrate, common high performance RF material. We've compared two different feed methods in Nullspace EM and CST. And there's so let's look at the S parameters first. See CST, Nullspace EM, and then we fabricated two patches and measured two patches independently. And so we see they all line up at the center frequency. Return loss is well predicted, particularly by Nullspace EM. And the gain pattern, when you take into account chamber artifacts, you can see the chamber set up here in the top right. The patch is on a 3D printed mechanical holder. It's not really a ground plane because it's plastic, but mounted here in the measurement fixture. So when we account for chamber artifacts, we got very good agreement between the predicted gain pattern and the measured performance. So we've kind of got our baseline here. So what we're going to see in general how a lens can improve the performance of this patch antenna, but then more specifically look at how what are the performance differences, pros and cons between a zone plate lens and a GRIN lens. So oftentimes when we do lens design, we first will do a plane wave analysis. And so a zone plate lens and a cylindrical GRIN lens are both semi-analytic cases. We have some design formulas for how to go about designing those. So we pick a focal length, 35 millimeters, pick a thickness. So both lenses are the same thickness. And we're going to assume that both lenses are made from Rogers Radix 2.8. And so as an initial assessment of the performance, we do a plane wave excitation and plot the near fields. And you can see here in the lower left, the near fields and how how each lens is focusing that plane wave illumination down to a spot size. And each lens has a focal length of approximately 35 millimeters. So right out of the gate, we basically have two kind of equivalent lenses, zone plate and GRIN, both occupying the same volume, both having the same thickness, both having the same focal length. So are there any performance differences between the two? So when we go to 3D print the cylindrical GRIN lens, so remember this zone plate lens is just solid, so there's no real question about fabricating that. But when we go to print the cylindrical GRIN lens, we have to consider the accessible ranges of dielectric values. And if you recall from the previous webinar, Phil talked about the range that you can access based on unit cell size, printed unit cell size in Radix 2.8. So we pick a unit cell size. In this case, we picked 6 millimeters. That unit cell size primarily is driven by some combination of geometry resolution and cutoff frequency. And you can see the cutoff frequencies here are well above our operational frequency of 16 gigahertz. So 6 millimeter unit cell size is going to work well for us. And in the lower right, you can see the accessible range of permittivity values when we 3D print a gyroid unit cell shape and vary the wall thickness. So we can't make the wall thickness too thin or it's not mechanically stable. So there's a lower limit, in this case about 1.24, and we can't make it too thick, or the pores in the gyroid actually close up and it becomes difficult to clean, etc. So there's an upper limit of about 2.37. And then of course we can always print a solid region. So 2.8 is accessible as well. So with all of these fabrication considerations in mind, we designed a 4-zone GRIN lens. The zone plate lens was also four subzones, and you can see the permittivities that are chosen for each of those layers according to the design formulas on the previous slide. And all of the permittivity values, fall within this 6 millimeter unit cell size. So just from a material selection and fabrication constraint standpoint, we're in good shape here with the cylindrical GRIN. So let's look at the simulated performance between both the zone plate lens and the cylindrical GRIN lens. So you can see the representation of each patch antenna and lens combination, and these are screenshots taken from Nullspace Prep. In the lower left, we see the return loss, and there's a lot of data on this going on this chart here, so let me explain a little bit. So we have the original patch CST model. We have the original patch Nullspace EM model. And then when we add in the zone plate lens or the GRIN lens, there's a question of, well, does that impact the return loss? And the answer is really no, not so much. And that's primarily due to the electrical separation between the patch and the lens. They're at 35 millimeter focal length, they're spaced far enough apart that there's not really an appreciable impact on return loss. And since we fabricated 2 patch antennas, we also fabricated 2 zone plate lenses and 2 GRIN lenses and did measurements of all of those. And you can see that all of the patch and lens combinations in terms of the measured data, they're all clustered together. So we've got good return loss, good model measurement agreement, expected behavior in terms of impact of the lens on the patch antenna's return loss. So everything is good there. But what we're really after is, what is that gain enhancement? So the patch antenna itself is typical patch antenna, 6 or 7 dB of gain. But when we add in the zone plate or the GRIN lens, they're occupying approximately the same volume. And we get a pretty nice gain enhancement, about 14 dB of gain enhancement over the patch by itself. And you'll notice a couple of things here. The GRIN lens actually gives a slightly higher bore sight gain, and at the same time, fairly significantly reduced backlobe. And there are a couple, so this is probably one of our first real performance difference between using a zone plate lens versus a GRIN lens. Part of the reasoning for this is that if you think of the zone plate lens, these outer rings are actual lower dielectric values. So as the phase front propagates out from the patch antenna, instead of impinging upon this slab of solid dielectric at a permittivity value of 2.8, it impinges upon a region of permittivity that's much lower than that, 1.3, 1.6, somewhere in there. And so the GRIN lens is actually allowing energy to it's a bit of an impedance matching benefit there. It's allowing energy to kind of soak into the lens more easily. So that's contributing both to the higher bore sight gain, but also to the lower backlobe. So, depending on the application, pretty nice benefit there in terms of the backlobe reduction. All right, so we've got some simulated data here. Now we want to go to fabrication. I won't dwell too much on this because Phil already talked about this a fair bit in the previous webinar, but the basic idea is you have the part design imported into the build file preparation software. You go through printing, then you have some curing and cleaning steps, and you end up with the final fabricated product. In the case of the GRIN lens, there's an additional step of doing the lattice design. So that's actually converting our layered representation into the gyroid representation, which you can see there in the top left. And then the rest of the process is essentially the same, print, clean, cure, etc. So then we took these fabricated lenses. We wanted to check the performance. So we took them to the chamber as well when we actually built models of the as-built lenses. So you see these models here, add in the structural support and this mounting structure. And we've got really nice agreement with the prediction and the measurement. There are some chamber artifacts. We've got all this structure here, but those are expected. So everything looks, looks how we would like it to. So in general, we've gotten through this case study. We've seen that you can represent the GRIN lens, and we've looked at a couple of voxelized cases. We've looked at in depth in some layered cases at this point, and we've seen that GRIN lenses, even though this is just one example, there were some notable performance differences and benefits between the GRIN lens and the zone plate lens. So, I feel at this point we've got another kind of tool in our RF design toolbox. We can add in because we've got the fabrication capability offered by Fortify and the design capability offered by Nullspace Prep and the results we can get from Nullspace EM. We've got a new tool that we can use to design new RF devices. Now I'll add one other small example here to kind of entice you as to the power of Nullspace Prep and EM. These lenses that we've looked at so far, even with this gradient index, this cylindrical gradient index lens, it's still what I would call a traditional GRIN lens. It is it's kind of a quasi-analytic design approach, still based loosely on Fresnel zones, and it's limited by some optical design constraints. And it occupies, in this case, almost a 4-inch cube working volume, a little bit less than that, but a 4-inch cube working volume. So if I have the power of controlling shape, dielectric choice, and gradient of that dielectric, can I do something novel to get similar or better performance, or improve upon the performance of that initial patch design without occupying so much volume? And again, we have to obey physics, but if we use the power of the Python API that runs throughout our tool chain, Nullspace Prep and Nullspace EM, it opens up a huge possibility for us in terms of design optimization and using our RF design intuition to then access non-traditional designs, instead of just leaning on kind of these, even though it's a fairly unique in terms of what you see out in the world these days. It's still a traditional cylindrical GRIN lens. In this case, we can leverage our intuition and design optimization capability offered by Nullspace to do some interesting new things. So just as a simple example, continuing with our 16 gigahertz patch antenna, we use a voxel-based optimization. So we specify a 1 by 8 by 8 voxel grid. So these voxels are not cubic voxels, they're rectangular prisms. And this 1 by 8 by 8 voxel grid occupies approximately a 1-inch cubic working volume sitting directly on top of that patch. The patch cross section is actually a little bit less than an inch, but the height of the cube is allowed to be an inch. And so we take this 8 by 8 voxel grid and printable material constraints, use the Python API in Nullspace Prep, and put this into an optimization workflow and ask Nullspace to design a gradient index structure. I won't call it a lens anymore. I'll just call it a GRIN structure that gives me a gain enhancement over that initial patch antenna design. And so you can see here the design that it came up with. It's a bit non-intuitive, but certainly provides, somewhere in the neighborhood of 7 dB of gain enhancement without really taking up any more space. We were already occupying, 20 millimeters or so of cross-sectional area, and we just said, well, if we can use 25 millimeters of height above the patch for this GRIN structure, what can we get? And get a pretty substantial gain enhancement for a fairly simple, easily fabricated geometry. So, we can use kind of our RF intuition here to say, well, it's still, moving in the direction maybe of something kind of reminiscent of a dielectric waveguide or a dielectric rod antenna, but through the power of the Python API and the optimization process, it's not limited to, textbook approaches like we might if we were trying to do this by hand. So, in summary, gradient index structures themselves provide you with a huge capability. And when you marry that design approach up with the Python API in the Nullspace product suite, you can come up with some pretty novel designs that give a huge performance improvement. So with that, I will conclude, and we'll take some Q&A. And if you missed parts 1 or 2 of the series, check them out on YouTube.
Thank you, Daniel. That was great. We have a few questions that have come in, so I can read those off. Is the CST simulations using the T or F solver?
We ran both cases.
And then this one has a specific slide it's referring to. In slide 17, what might be the reason for the S11 response different simulation softwares?
There are a lot of factors that go into that. There, the way the excitation actually is implemented is a difference driver. In CST, you get radiation box effects that will impact the return loss as well. So, the short answer is there are a handful of things that contribute to that.
Okay, fantastic. And then we have a few more. Have you compared the weight/mass of the GRIN lens versus zone plane lenses?
Yeah, good question. So interestingly, they use about the same amount of resin, so they actually weigh the same. That won't necessarily always be true, but that just happened to be true in this case. Certainly in an optimization context, you could add that as a variable in your optimization process for a GRIN structure.
Okay, thank you. We're running short on time, so I'll read the next one. Can you explain how the optimized antenna on the last slide works? Why is optimization helpful in that case?
Yeah, so we when we have moved into this realm of, I want to use the working volume in the very near field region of that patch antenna. uh, there aren't a lot of kind of what I'll just call textbook designs um, for how to get a gain enhancement there. So we know that through concepts like a GRIN lens or even a dielectric rod antenna or a GRIN type rod antenna, that there is an intuition that says something can be done. But the problem is I don't know necessarily what shape to draw, and as soon as I draw a specific shape, I'm limited to that parameter representation of that shape. So instead of doing that and limiting myself perhaps to the wrong thing right out of the gate, instead I can use my intuition and the Python API and say, well, I'm going to represent this as a series of voxels, and I'm going to allow the material selection still within that printable range of the radix on the Fortify platform, and the optimizer will find a design, and oftentimes it comes out with these somewhat non-intuitive cases.
Thank you. Someone was wondering if we provide design consulting services or if it's just the software.
Yeah, we do provide consulting services. We work with different customers and can help them, particularly with kind of these unique design optimization problems. We've got a lot of engineering experience across both design, simulation, fabrication, measurements, designing for real world constraints, etc. So, we're happy to help out.
Okay, we have a couple more. Try to get through these. Does Nullspace have ability to extract effective medium properties from the unit cell?
Uh, Nullspace EM itself doesn't provide that capability, but through the Python API, you can basically build an optimization wrapper around the simulation to do an extraction. And we certainly have done that before, to have it, based on some measured data, do a CEM based effective media extraction.
And we're happy to work with you to build that out too.
Yeah.
Okay, and then on the last slide, what are the permittivity values and voxel grid that the voxel grids have? I think I messed up some of those words, sorry.
Yeah, they they range between 1.3 and 1.3 and 2, and then we also allow 2.8. So everything you see there in that image is between 1.3 and 2 or 2.8.
Okay, and then what was the simulation duration with and without lenses, time taken for simulation, any mesh constraints in the software?
Yeah, so the patch antenna by itself takes a few seconds to run. When you add in the lenses, when we're in this kind of setup, this is on the order of a few minutes. And we add in some additional structure, as fabbed. I don't recall right off the runtime, but on a laptop, it's maybe 10 minutes or so.
Okay, if anyone has any more questions, feel free to pop them in the chat or the Q&A. And I just want to remind everybody on the call, if you're interested in a free trial, please visit our website. It's right in the top. We're happy to get that set up for you, or just contact us directly from any of the webinar emails. We can get that going for you. With that,
Jessica, can I just jump in since we're wrapping up our three-part series with Fortify? I just want to jump in and thank our partners at Fortify and bringing together the series of webinars. I think it was really interesting, and we had a lot of people excited about new tools that are now becoming available, like Nullspace for simulation, like Fortify's services and 3D printing services and manufacturing services. So exciting times in the space of RF. And for everyone here, again, as Jessica mentioned, if you're interested in having a demo of Nullspace, please reach out. We're happy to set up a free trial for you guys as well. And as Jessica mentioned, on our website, it's www.nullspaceinc.com. There's a big button that says request a demo. If you push on the button, just fill out the form and we'll get back to you right away. Daniel, thank you for that presentation. Jessica, thank you for the hosting. Thanks to our friends at Fortify. And we hope to see you all in future webinars.
Yeah, thanks everybody.
Yeah.